Hello everyone, I'm Professor Diwa, and welcome to a math video on simplifying radical expressions. Our objectives are to use the product rule for radicals, use the quotient rule for radicals, simplify radicals, use the distance and midpoint formulas. Alright, so let's get started. First, we have the product rule for radicals. Here it states if the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b is equal to the nth root of a times b. So according to the product rule for radicals, if we have a product between two radicals with the same index n, then we could combine everything under one radical with the same index n. For example number 1, multiply the following. For part A, we have the cube root of 2 times the cube root of 13. For this problem, we need to use the product rule for radicals. Since we have a product between two radicals with the same index, we could just combine everything under one radical. So we get the cube root of 2 times 13. Next, we simplify by multiplying 2 times 13, which is 26. So our final answer is the cube root of 26. Moving on to part B, we have the square root of x minus 3 times the square root of x plus 3. Again, we need to use the product rule, so we could rewrite this product under one radical. This is the square root of parentheses x minus 3 times parentheses x plus 3. Next, we simplify the inside of the radical by multiplying x minus 3 and x plus 3 together. This is a difference of squares, so we get x squared minus 9. Our final answer is the square root of x squared minus 9. For part C, we have the fifth root of 6 times c times the fifth root of 7 times c squared. Again, we just apply the product rule. We get the fifth root of 6c times 7c squared. Next, we simplify the inside by multiplying together the 6c times 7c squared. We get 42c cubed. Our final answer is the fifth root of 42c cubed. Next, we have a practice problem. Simplify the following. For part A, we have the square root of 11 times square root of 7. For part B, we have the square root of x minus 5 times square root of x plus 2. For part C, we have the seventh root of 5p times the seventh root of p cubed. Alright, so go ahead and pause the video, simplify each problem, and then check back with the video to see the solutions. Alright, so let's get started with part A. First, we apply the product rule, so we get the square root of 11 times 7. Simplifying the inside of the radical, we get 11 times 7 is 77, so the final answer is the square root of 77. Moving on to part B, again we apply the product rule. So we have the square root of parentheses x minus 5 times parentheses x plus 2. Next, we simplify the inside of the radical by multiplying the x minus 5 and the x plus 2 together. We get our final answer, which is the square root of x squared minus 3x minus 10. Moving on to part C, again we apply the product rule. We have the seventh root of 5p times p cubed. Multiplying 5p and p cubed together, we get 5p to the fourth power. Our final answer is the seventh root of 5p to the fourth power. For example number 2, simplify. Assume that all variables represent positive real numbers. For part A, we have the square root of 18. What we need to do first is break this up into two numbers, where one number is a perfect square. So I rewrote 18 as 9 times 2. So we have the square root of 9 times 2. Next, we're going to use the product rule for radicals. We can take our single radical and rewrite it as two separate radicals. So I have the square root of 9 times the square root of 2. When we take the square root of 9, we get 3, and then we bring down the root 2. So our final answer is 3 root 2. Moving on to part B, we have 5 times the cube root of 24. We need to rewrite 24 as the product of two numbers, where one number is a perfect cube. So I rewrote 24 as 8 times 3. So I have 5 times the cube root of 8 times 3. Next, we use the product rule to rewrite the radical as two separate radicals. So I have 5 times the cube root of 8 times the cube root of 3. Next, we could simplify by taking the cube root of 8, which is 2. So I have 5 times 2 times the cube root of 3. Next, we multiply the 5 times 2, which is 10, and then we bring down the cube root of 3. So our final answer is 10 cube root of 3. Moving on to part C, we have the square root of 128x squared. To simplify this radical, we need to rewrite 128 as the product of two numbers, where one number is a perfect square. So I chose to rewrite 128 as 64 times 2. So I have the square root of 64 times 2x squared. Next, we can use the product rule to break apart this radical into 3 separate radicals. However, this step isn't necessary, but I'm just showing it to you so you can see how this works. In the future, you're going to see me skip this step because it becomes very cumbersome, especially when you have multiple terms underneath the radical, like in part D. Alright, so again, using the product rule, I could rewrite this as the square root of 64 times the square root of 2 times the square root of x squared. Next, we take the square root of 64, which is 8, the square root of x squared, which is x, and then we bring down the root 2. So our final answer is 8x root 2. Moving on to part D, we have the cube root of 27 m to the 4th power n to the 14th power. To simplify this, I'm going to rewrite everything underneath the radical. Starting with 27, 27 is a perfect cube. We could rewrite this as 3 cubed. Moving on to m to the 4th power, we need to rewrite this as a product of two variables, where one variable has the largest exponent that we can make from 4, which is a perfect cube. So I rewrote m to the 4th power as m cubed times m. Moving on to n to the 14th power, we need to rewrite this as a product of two variables, where one variable has the largest exponent we can make from 14, that is a perfect cube. So I rewrote n to the 14th power as n to the 12th power times n squared. Next, we just take the cube root of each term under the radical. So the cube root of 3 cubed is 3, the cube root of m cubed is m, the cube root of n to the 12th power is n to the 4th power, and then everything else will stay under the radical. So we bring down the cube root of m times n squared. Our final answer will be 3m n to the 4th power cube root of mn squared. Next, I'm going to show you an alternative way to simplify part D. First, I'm going to rewrite 27 as 3 cubed. So we have the cube root of 3 cubed, m to the 4th power, n to the 14th power. Next, we're going to convert our radical into a rational exponent. If you forgot how to do this, we have the formula for the conversion up here. The nth root of a to the m is equal to a to the m over n power. So we get 3 to the 3 over 3 power times m to the 4 over 3 power times n to the 14 over 3 power. Next, we simplify. So 3 to the 3 over 3 power is the same thing as taking the cube root of 3 cubed. We just take the exponent 3 and divide it by the index 3, which would be 1. This means we have 3 to the 1 power, or just 3, on the outside of the radical. Moving on to our next term, we have m to the 4 over 3 power. We just take the exponent of 4 and divide it by the index of 3. So 3 goes evenly into 4 one time. So this means we could just take 1m outside of the radical, and then we also have a remainder of 1. The remainder tells you how many m's you have left on the inside of the radical. Since the remainder is 1, we have m to the 1 power, or just m, left inside the radical. Next, we have n to the 14 over 3 power. This is the same thing as just taking the cube root of n to the 14th power. We just divide the exponent of 14 by the index of 3. 3 goes evenly into 14 4 times. So we have n to the 4th power on the outside of the radical. And the remainder is 2. So the remainder tells you how many n's we have left over underneath the radical, which is going to be n squared. So our final answer is 3m n to the 4th power times the cube root of mn squared. Next, we have a practice problem. Simplify. Assume that all variables represent positive real numbers. For part A, we have the square root of 48. For part B, we have 4 times the cube root of 54. For part C, we have the square root of 18x to the 6th power. For part D, we have the fourth root of 16, a to the 5th power, b to the 11th power. Alright, so go ahead and pause the video, try out this problem, and check back with the video to see the solutions. Alright, so let's go ahead and go over the solutions. For part A, I rewrote 48 as 16 times 3, so I have the square root of 16 times 3. Next, we could break apart the radical using the product rule, or you could skip this step, it's up to you. We get the square root of 16 times the square root of 3. Next, we simplify. The square root of 16 is 4, and then we bring down root 3. So our final answer is 4 times root 3. Moving on to part B, I rewrote this as 4 times the cube root of 27 times 2. Next, we could break apart the radical using the product rule. Again, you're welcome to skip this step if you like. We get 4 times the cube root of 27 times the cube root of 2. Next, we simplify by taking the cube root of 27, which is 3, and then bring down the 4 and the cube root of 2. We get 4 times 3 times the cube root of 2. Next, we multiply 4 times 3, which is 12, and bring down the cube root of 2. So our final answer is 12 cube root of 2. For part C, I rewrote this as the square root of 9 times 2, x to the 6th power. Next, I use the product rule. I have the square root of 9 times the square root of 2 times the square root of x to the 6th power. Taking the square root of 9, we get 3. Taking the square root of x to the 6th power, we get x cubed. And then we bring down the square root of 2. Our final answer is 3x cubed square root of 2. Moving on to part D, I rewrote 16 as 2 to the 4th power. I rewrote a to the 5th power as a to the 4th power times a. I rewrote b to the 11th power as b to the 8th power times b cubed. So I have the fourth root of 2 to the 4th power times a to the 4th power times a times b to the 8th power times b cubed. Next, we could go ahead and simplify by taking the fourth root of each term. The fourth root of 2 to the 4th power is 2. The fourth root of a to the 4th power is a. The fourth root of a will stay the same. We get the fourth root of b to the 8th power is b squared, and the fourth root of b cubed will stay the same. So our final answer is 2ab squared times the fourth root of ab cubed. If you wanted to simplify this using the alternative method, you could rewrite part D as 2 to the 4 over 4 power times a to the 5 over 4 power times b to the 11 over 4 power. Simplifying 2 to the 4 over 4 power, 4 divides evenly into 4 one time, so we just get 2. Next, we simplify a to the 5 over 4 power. 4 goes into 5 evenly one time, so we get 1a outside the radical, and we have 1a remaining on the inside of the radical. For b to the 11 over 4 power, 4 goes evenly into 11 two times, so we get b squared on the outside of the radical, and we have a remainder of 3, which gives us b cubed left over on the inside of the radical. So our final answer is 2ab squared times the fourth root of ab cubed. For example number 3, multiply and simplify. Assume that all variables represent positive real numbers. For part A, we have 3 times the cube root of 4x times the cube root of 2x to the 4th power. The first step is combining everything under one radical by using the product rule. We get 3 times the cube root of 4x times 2x to the 4th power. Next, we simplify by multiplying the 4x and the 2x to the 4th power. We get 3 times the cube root of 8x to the 5th power. Next, I rewrote x to the 5th power as a product of two variables, where the exponent of one variable is a perfect cube, which is x cubed times x squared. So we have 3 times the cube root of 8x cubed x squared. Next, we could go ahead and take the cube root of 8, which is 2. the cube root of x cubed, which is x, and then we bring down the 3 and the cube root of x squared. So we have 3 times 2x times the cube root of x squared. Next, we multiply 3 times 2x, which is 6x. Our final answer is 6x times the cube root of x squared. Moving on to part B, we have the fourth root of 27a squared b to the 5th power times the fourth root of 6a cubed b to the 6th power. First, we use the product rule to combine everything together under one radical. We get the fourth root of 27a squared b to the 5th power times 6a cubed b to the 6th power. Next, we multiply everything together underneath the radical. We get the fourth root of 162 a to the 5th power b to the 11th power. Next, I rewrote 162 as a product of two numbers where one number is a perfect square, so I have 81 times 2. Next, I rewrote a to the 5th power as a product of two variables where one variable has the largest exponent we can make out of 5, which is a perfect fourth power. So I have a to the 4th power times a. Next, I rewrote b to the 11th power as a product of two variables where one variable's exponent is the largest perfect fourth power we can make using 11. We get b to the 8th power times b cubed. Next, we go ahead and take the fourth root of each term. The fourth root of 81 is 3. The fourth root of 2 will stay the same. The fourth root of a to the 4th power is a. The fourth root of a will stay the same. The fourth root of b to the 8th power is b squared. The fourth root of b cubed will stay the same. So our final answer is 3ab squared times the fourth root of 2ab cubed. Next, we have a practice problem. Multiply and simplify. Assume that all variables represent positive real numbers. For part A, we have the cube root of 12a squared times the cube root of 10a to the 4th power. For part B, we have 4 times the cube root of 8a squared b to the 5th power times the cube root of 6a squared b to the 4th power. Alright, so go ahead and pause the video, work out these problems, and check back with the video to see the solutions. Alright, so let's get started with part A. First, I use the product rule to rewrite everything under one radical. So I have the cube root of 12a squared times 10a to the 4th power. Next, we multiply the terms underneath the radical together. We get the cube root of 120a to the 6th power. Next, I rewrote 120 as a product of two numbers where one number is a perfect cube. So I have the cube root of 8 times 15a to the 6th power. Next, we take the cube root of 8, which is 2. The cube root of a to the 6th power is a squared, and then we bring down the cube root of 15. Our final answer is 2a squared times the cube root of 15. Moving on to part B, we use the product rule to rewrite everything under one radical. We have 4 times the cube root of 8a squared b to the 5th power times 6a squared b to the 4th power. Next, I multiplied everything together underneath the radical. However, I kept 8 and 6 separated. So I have 4 times the cube root of 8 times 6a to the 4th power b to the 9th power. Next, I rewrote a to the 4th power as a cubed times a. So we have 4 times the cube root of 8 times 6a cubed times a times b to the 9th power. Next, we simplify. The cube root of 8 is 2. The cube root of a cubed is a. The cube root of b to the 9th power is b cubed. And then we bring down the 4 and the cube root of 6a. So we have 4 times 2ab cubed times the cube root of 6a. Next, we multiply 4 times 2ab cubed. We get our final answer is 8ab cubed times the cube root of 6a. Next, we have the quotient rule for radicals. It states if the nth root of a and the nth root of b are real numbers, and the nth root of b is not 0, then the nth root of a over b is equal to the nth root of a over the nth root of b. So according to this rule, if we have the nth root of a over b, this could be split up into two separate radicals. the nth root of a over the nth root of b. In the next set of examples, we're going to use the quotient rule for radicals to help us simplify the problems. In example number 4, simplify. Assume that all variables represent positive real numbers. For part A, we have the square root of 18 over 25. The first step here to simplify is to use the quotient rule to break apart this radical into two separate radicals. We get the square root of 18 over the square root of 25. Next, I rewrote the square root of 18 as the square root of 9 times the square root of 2. So we have the square root of 9 times the square root of 2 divided by the square root of 25. Next, we simplify. The square root of 9 is 3, and we could take the square root of 25, which is 5. So our final answer is 3 root 2 over 5. Moving on to part B, we have the cube root of 6z cubed over 125b to the 6th power. First, we use the quotient rule to separate the radical into two separate radicals. We have the cube root of 6z cubed over the cube root of 125b to the 6th power. Next, we could simplify the numerator by taking the cube root of z cubed, which is z. In the denominator, we could take the cube root of 125, which is 5, and the cube root of b to the 6th power is b squared. So our final answer is z times the cube root of 6 over 5b squared. Next, we have a practice problem. Simplify. Assume that all variables represent positive real numbers. For part A, we have the square root of 13 over 49. For part B, we have the cube root of 27p cubed over 8q to the 9th power. Alright, so go ahead and pause the video, try out this problem, and check back with the video to see the answers. Alright, so let's go over the solutions. For part A, I rewrote this as the square root of 13 over the square root of 49, and then we simplify by taking the square root of 49, which is 7. So our final answer is the square root of 13 over 7. For part B, I rewrote this as the cube root of 27p cubed over the cube root of 8q to the 9th power. Next, we could take the cube root of 27, which is 3, the cube root of p cubed is p, the cube root of 8 is 2, the cube root of q to the 9th power is q cubed. So our final answer is 3p over 2q cubed. In example number 5, simplify. Assume that all variables represent positive real numbers. For part A, we have the square root of 24a cubed divided by square root of 6a. To simplify this radical expression, we're going to use the quotient rule to rewrite this as one single radical. We have the square root of 24a cubed divided by 6a. Next, we could simplify the inside of the radical. 24 divided by 6 is 4. A cubed divided by a is a squared. So the result is the square root of 4a squared. Next, we take the square root of 4a squared. We get our final answer, which is 2a. Moving on to part B, we have the cube root of negative 375 x squared y divided by cube root of 3x to the negative 1 power y to the 7th power. Again, we're going to use the quotient rule to combine the two radicals into one radical. We get the cube root of negative 375 x squared y divided by 3x to the negative 1 power y to the 7th power. Next, we go ahead and do the division. Negative 375 divided by 3 is negative 125. For x squared divided by x to the negative 1 power, when we divide the bases of exponents, we take the base x and then we subtract the exponents. So we have 2 minus a negative 1. 2 minus negative 1 is positive 3, so we get x cubed. Next, we have y divided by y to the 7th power. Again, we're going to subtract the exponents. So 1 minus 7 is negative 6. So we get y to the negative 6th power. The result is the cube root of negative 125 x cubed y to the negative 6th power. Next, we take the cube root of negative 125, which is negative 5. The cube root of x cubed is x. And the cube root of y to the negative 6 power is y to the negative 2 power. The result is negative 5 xy to the negative 2 power. From here, we need to rewrite everything with positive exponents. So we can rewrite y to the negative 2 power as its reciprocal with a positive exponent. So our final answer is negative 5x over y squared. Next, we have a practice problem. Simplify the following. For part A, we have the cube root of negative 24x squared over cube root of 3x to the negative 1 power. For part B, we have the cube root of negative 250 a to the 5th power b to the negative 2 power over cube root of 2ab. Alright, so go ahead and pause the video, simplify each problem, and then check back with the video to see the solutions. Alright, so let's go over part A. First, we use the quotient rule to rewrite everything under one radical. We have the cube root of negative 24x squared over 3x to the negative 1 power. Next, we do the division. Negative 24 divided by 3 is negative 8. X squared divided by x to the negative 1 power is x cubed. The result is the cube root of negative 8x cubed. Next, we can take the cube root of negative 8x cubed. The final result is negative 2x. Moving on to part B, we could rewrite everything under one radical using the quotient rule. We have the cube root of negative 250 a to the 5th power b to the negative 2 power over 2ab. Next, we do the division. Negative 250 divided by 2 is negative 125. A to the 5th power divided by a is a to the 4th power. B to the negative 2 power divided by b is b to the negative 3rd power. The result is the cube root of negative 125 a to the 4th power b to the negative 3rd power. Next, we take the cube root of negative 125, which is negative 5. Next, we take the cube root of a to the 4th power. We just take the exponent 4 and divide it by 3. 3 goes into 4 one time, which means we have 1a on the outside of the radical, and we have a remainder of 1, which means we still have 1a underneath the radical. Next, we take the cube root of b to the negative 3 power, which is b to the negative 1 power. The result is negative 5 ab to the negative 1 power times the cube root of a. From here, we need to rewrite b to the negative 1 power as a positive exponent. So our final answer is negative 5a times the cube root of a divided by b. Next, we have the distance formula. It states here that the distance d between any 2 points, parentheses x1, y1, and parentheses x2, y2, is given by the equation d equals the square root, parentheses x2 minus x1, and we have a square on the parentheses, plus, parentheses, y2 minus y1, and a square on the parentheses. In the next example, I'm going to show you how we apply the distance formula. In example number 6, find the distance between the given points. Give an exact answer and an approximation to 3 decimal places. We have the points 5, negative 1 and negative 4, 6. 5, negative 1 will be my x1, y1, and negative 4, 6 will be my x2, y2. All we need to do to find the distance between these 2 points is plug in those values into the distance formula. So we have d equals the square root of parentheses, negative 4 minus 5, and then we have a square on the parentheses, plus parentheses, 6 minus negative 1, and then a square on the parentheses. Next, we simplify the inside of the parentheses. Negative 4 minus 5 is negative 9. 6 minus a negative 1 is positive 7. The result is the square root of negative 9 squared plus 7 squared. From here, we square the negative 9, which is 81, and square the 7, which is 49. The result is the square root of 81 plus 49. Next we add 81 and 49, which is 130. So our final answer is the square root of 130 units. This is the exact answer. The problem also wants an approximation to 3 decimal places. So after taking the square root of 130 and rounding the value to 3 decimal places, we get 11.402 units. Next, we have a practice problem. Find the distance between the given points, give an exact answer, and an approximation to 3 decimal places. We have the 2 points, 4, 5, and 7, 1. Alright, so go ahead and pause the video, try out this problem, and check back with the video to see the solutions. Alright, so let's go ahead and go over the practice problem. So we just take our points, 4, 5, and 7, 1, and plug them into the distance formula. We get d equals square root, parentheses, 7 minus 4, and then a square on the parentheses, plus, parentheses, 1 minus 5, and a square on the parentheses. Next, we simplify all the terms inside the parentheses. 7 minus 4 is 3, 1 minus 5 is negative 4. We get the square root of 3 squared plus negative 4 squared. Next, we simplify everything under the radical. 3 squared is 9, negative 4 squared is 16, and then we just add 9 plus 16, which is 25. So the result is the square root of 25. Next, we take the square root of 25, which is 5. So our final answer is 5 units. Next, we have the midpoint formula. It states here that the endpoints of a segment are the points parentheses x1, y1, and parentheses x2, y2. Then the coordinates of the midpoints are parentheses x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. You could think of the midpoint formula as just the average value of the x-coordinates and the average value of the y-coordinates. In example number 7, find the midpoint of the segment with the given endpoints, parentheses negative 2, 3, and parentheses 4, negative 6. To find the midpoint of the segment, we just take our 2 points and substitute the values into the midpoint formula. Negative 2, 3 is my x1, y1, and 4, negative 6 is my x2, y2. We get parentheses negative 2 plus 4 divided by 2, comma, 3 plus negative 6 divided by 2. Simplifying the first fraction, negative 2 plus 4 is 2, so we have 2 over 2 for the x-coordinate. Simplifying the second fraction, 3 plus negative 6 is negative 3. So for the y-coordinate, we have negative 3 over 2. Next, we simplify. 2 divided by 2 is 1, and negative 3 over 2 stays the same. So the final answer for our midpoint is parentheses 1, negative 3 over 2. Next, we have our practice problem. Find the midpoint of the segment with the given endpoints. Parentheses negative 2, 5, and parentheses 8, 3. Alright, so go ahead and pause the video, find the midpoint, and then check back with the video to see the answers. Alright, so let's go over the solutions. First, we just substitute our points into the midpoint formula. We get parentheses negative 2 plus 8 divided by 2, comma, 5 plus 3 divided by 2. After simplifying the fractions, we get parentheses 6 divided by 2, comma, 8 divided by 2. Next, we just do the division. 6 divided by 2 is 3, 8 divided by 2 is 4. Our final answer for the midpoint is parentheses 3, 4. Alright, well this is the end of our video. Thank you very much for watching. I'm Professor Diwa, and I'll see you in the next one.